Hello, I'm Ed Pegg Jr., and welcome to another episode of Mathematical Games, a series that covers the work of Martin Gardner, who was famous for his series, Mathematical Games and Scientific American. And I'll be talking about mathematical constants today. We have many demonstrations that deal with various constants. Here's a few of the ones dealing with pi, and pretty much any famous constant you can put in, we've got a demonstration. And here's the really famous constants that we have symbols for, pi and e, Euler E being two of the big ones, but we've also got other famous constants such as the golden ratio, the Catalan constant, Euler gamma, and I'll be covering those and others today. So in Mathematica, we currently have 436 math constant entities, and here's a list of them, like the Gauss constant or the nested radical. We've got a whole bunch here, and I'll try to cover some of these today, the silver root. So I'll be trying to cover some of these constants today. And here's some of the constants that are easier to express. For example, the Froda constant is 2 to the e, reciprocal of pi. The Apri constant is zeta 3, and I'll be covering that. We've got a whole bunch of different constants, and these are the ones that are a little bit easier to represent exactly. I did not list in this table the ones that don't have an exact representation, or that the column over here would fill several pages, such as the Conway constant, which is a order 76 polynomial root. So I'll start by talking about the Kenshin constant, which is a somewhat amazing constant dealing with continued fractions. So if you take a continued fraction such as pi or e, the continued fraction is a way of expressing the number as a fraction. And there's various terms that come out of it. If it's a not a quadratic, such as the golden ratio, then you'll get a whole bunch of different numbers with seemingly no pattern. But if it's a quadratic, then there's a regular pattern to it. Such as these. Now I'm not sure how long this one takes to repeat. Might be quite a bit. Then maybe this one doesn't repeat. I think that's a quadratic. But if you take one of these values, for example, um, I had pi here, the continued fraction. Let's try it with this instead. Okay, this is going to Kenshin's constant, so maybe it is not repeating. And basically for almost any real numbers, real number, when you perform this for some value, for example, e plus pi, it usually will go to the same number, which is Kenshin's constant. And there's a bunch of various related constants to Kenshin's constant. So if we plot this, we get that as you use more and more and more terms, it goes to Kenshin constants. So the geometric mean for pi is that if we use a different value, such as Kenshin constants itself, it's still going towards the value. And you can basically put in any number that's not, say, a rational or a quadratic, and if you take if you multiply all these terms into continued fraction and you raise it to the length of the number of terms you used, it will always go to the same value, which is Kenshin's constant, which is something I find unbelievable. But apparently that's a certain property of continued fractions that comes out. So there's a few core transcendental numbers, such as pi and e and the golden ratio. Martin Gardner wrote about them. For example, here's his talk about pi, and here's his talk about, I believe, the golden ratio. Oh no, this is his talk about e. Any of these transcendental numbers you could discuss at length to fill a book. In fact, I believe pi and e and the golden ratio and I all have their own books dedicated to them. And one particular set that I like quite a bit is the golden ratio, the plastic constant, the super golden ratio, and related items. Here's a few of those constants here. And here's Gardner's discussion of the golden ratio. I did a whole talk about these, one of my first talks, algebraic number magic. And this talk will be given in Wolfram Community sometime either today or tomorrow. But I can show a few highlights of some of these. For example, the plastic constant is the smallest Poisson number, and it's the x to the third equals x plus 1. It's a root of that. And here's a value in radicals. You can divide up a square into 3 rectangles that have the ratio of the plastic constant. And we can express the Padovan sequence or the parent sequence, both of which have ratios going to the plastic constant. One start 1, 1, 1, 2, 2, 3, 4, 5, 6, and basically what you're doing is you're adding terms from either the last 2 terms, or you're skipping slightly different. So 3. So basically you're going back before the previous term. So 3 plus 0 is 3, 0 plus 2 is 2, 2 plus 3 is 5, and so on. And one thing you can do with that constant, if you use powers of the square root of that, the square root of the plastic constant to the power of 0, 1, and 4 gives this triangle. And all of these triangles here are powers of the square root of the plastic constant. You can divide up the triangle itself, it's self-similar, into these different triangles, and then you can rearrange it to make this triangle with the same triangles. So this is a way of cutting a triangle into 6 similar triangles and recreating itself in 2 different ways. I believe this is one of the few triangles where you can do that. And here's a geometric scene which solves the problem. If we take a complex root of the plastic constant of is a complex root of x to the third equals x plus 1. If you take the fourth root and the seventh root and so on, you get these points in the plastic fractal triangle, which I show here. And if you use an infinite number of them, starting with the fourth power and then everything thereafter, they will combine to make a copy of the plastic fractal triangle. And here's other roots. So the square root of the plastic constant to the 0, to the 1, to the 2, to the 3, to the 4, to the 5, to the 6, to the 7, to the 8. You can combine them to make this figure, and it's a pentagram of powers of the square root of the plastic constant, where they're all different except for the repeated 3. I don't know of any other constant where you can do that. And you can go to 19 points in 3D space, and all 19 points are powers of the square root of the plastic constant away from each other. So this is a way of doing K19 with powers of a particular value. And I'm positive that the plastic constant is the only number with that property. We can also divide up a rectangle into similar triangles and do a progression of them. And there's a whole series. Here's the plastic constant at the top. Here's the super golden ratio next. This is the chi constant here. So there's a whole series based on Bezout numbers that you can do geometric tricks with. And the next one here is, I can open it. It doesn't want to open. So the golden ratio, here's the continued fraction. It's all ones. It's the ratio of terms in the Fibonacci sequence, and almost all of the different regular dice. These are the complements of Archimedean solids and a few other shapes. Can all be built with coordinates using the golden ratio. The almond chair is a self-similar dissection, and the sides are powers of the square root of the golden ratio. And I put in various values here, which are powers of the square root of the golden ratio between points. There's quite a few places where powers show up in the diagram. The best 4-row solution with 16 lines and 15 points, you can represent completely with using the golden ratio. I call it this phi space because all coordinates are based on the golden ratio. And here are 3 more figures in orchard planting that are based on the golden ratio space. And for the silver ratio, that is the domain of the octagon. If you look at these points here, these are all expressible in terms of the silver ratio, 1 plus the square root of 2. A4 paper, which is used in Britain and places, it has the property that if you fold it in half, you get a rectangle which is similar to the original sheet of paper. So A4 paper has that property. And if you use a sheet of A4 paper with an area of 200, you can split it up into these rectangles, which are all either powers or twice a power. These are all of these rectangles are similar to each other. They're all basically A4 rectangles. We can also take a look at this triangle where all the numbers on the edges are powers of the square root of 2. this is a way of surrounding a point with similar triangles. For example, this side is length 1, this side is length square root of 2, I think, and this one is length 2. And this gives a weird way of dividing up a 4, 5, 6 triangle as shown here. So this is length 4, length 5, and length 6. And this is a bizarre way of dividing that triangle up into similar triangles. We can also divide up a rectangle into a series of similar triangles like this. And the 27 lines of a club surface are all in the golden, are all in the, not golden. Oh yes, it is. This is the golden ratio. Well, this should be in this one here then. Another constant is the Euler gamma constant. So if we take the harmonic series and add up all values, such as 1 plus a half and so on, we get this total, which is the 10th harmonic number. If we subtract log 10 from this, we get this value. And if we increase the number, it keeps going down more and more. If we go look at the 10,000th harmonic number minus log 10,000, we get 0.577. And somehow Euler noticed that this goes to a constant value, which is known as Euler gamma. So one way of expressing Euler gamma is with this sort of series here. So this value here is what's known as the Stirling constant, square root of 2 pi. The hyperfactorial goes to the Glacier constant, which is a approximation to the Stirling constant. And the related French and Robinson constant is the area under the gamma function, which is related to factorials. So here's a different constant, the Kontorovich O constant. So we start by taking a circle packing, and we've got a lot of them here. We basically take any of these circle packings. So here's the first one. It's a 2, 2, 3, 3, 6, 6, 6, 6, and 4 11s. If we list these out with multiplicity, 2, 2, 3, 3, 6, 6, 6, 6, 7, 11, 11, we can look at the growth rate of the terms. And it turns out that it's about 0.042 x to this value delta. If we look at a more complex one, such as a little bit further on, we get this series of circles, and it turns out that's equal to this coefficient x to this value delta. And delta is a constant for any circle packing like this. It's about 1.30568. So this is a constant. You just basically look at the number of terms for here, and you raise that's like the 7th term to this power. And for example, if you look at the 9th term here, it's about 0.0429 to the power of this. So that, I thought that was a very strange constant. Various metric constants, such as the Levy constant. Um, Tension-Levy is the nth root of the denominator of the nth continued fraction, and it converges to this value. The Levy constant is just the exponent itself. So we can look at these convergence for pi, such as this. Here's the constant here, and as we look at the convergence as we use more and more of them, the denominator, you can see that it's starting to hover around the constant. The exponent alone is the Levy constant. The Lou-Roth analogs, I tried to come up with a simple explanation for these, but it's basically a way of chopping up the unit interval, and I wasn't able to completely understand it, so I'm just putting it up as this table here. One of the reasons I do these talks is to try to teach myself these mathematical items, but often I run out of time to completely understand how something like the Loc constants work. Let's see, the Loc constant, if we want to get a number of continued fraction terms that will give us enough decimal places, the number of terms you need is basically based on Loc's constant. It's almost it's a 0.097. So if you have about 20 terms, you probably have of the continued fraction, you probably have enough terms to express the decimal. So the 20th convergent of pi gives 20 decimals of accuracy. That's what we see here. But in fact, the 19 terms of the continued fraction convergent is also enough to give 20 decimals of accuracy. But it's a near thing. But due to Loc's constant, this is the decimal version for base 10. The Loc constant basically tells you how many different terms of the continued fraction you need to express the decimal digit. The Champernowne numbers string together digits. For example, for base 10, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the numbers in base 10 all jammed together as a decimal. And the different Champernowne constants here use different bases. And we can make a grid of the values of these. One property of the Champernowne numbers is their continued fractions somewhat explode. They don't behave normally. Somewhere I've seen a mathematical discussion for how to get the next term in this series, but I wasn't able to find it before this talk. I think Maxim Ryden wrote it, but I wasn't able to find what it is. But it's a very large number. I should probably just take this value and put it into OAIS, and it'll probably tell me what the value is. The prime constant is a binary representation of the prime numbers. The position of the ones is where the primes are in the binary representation. And we can reverse it, and we get the values of primes out from the constant. One reason I made this the topic of my talk is because I came across a paper by Stephen Finch where he had a whole bunch of new constants in this paper here. And this talk will be online sometime today or tomorrow at community at wolfram.com. So you'll be able to see these links there as well. Let's see. One quick aside is back in the 1600s, John Wallace used Newton's method to solve this particular cubic. X to the third equals 2x squared plus 5. And with Newton's method, he was able to find this root to some number of places. I found it very interesting that the Rotund constant, which is mentioned in Finch's paper, is another cubic, which is just 4 away. So this is x to the third equals 2x squared plus 1 instead. And you get this value for that constant. Well, it turns out that this constant is a way of looking at random Fibonacci paths. And when you plot it out, here's a random Fibonacci path that hovers around the Rotund constant. There's automatic sequence constants. For example, the Thu constant is given by this series of nestings. And as you continue increasing the number of terms, you get this weird self-repeating constant. And when you plot it out, you get this weird pattern if you group them in blotches of 32. So all of these automatic sequence constants have odd patterns to them when you make arrays out of them. Some of the prime pattern constants, if we look at the sum of the reciprocals of the primes, they are close to log of the largest prime. And we can plot out how those are compared to each other if we take the approximation of log and also subtract log of pi squared over 6, as Euler did. The difference between the log and the sum of prime reciprocals is actually Merton's constant, which I show here. So let's see. Another one with primes is the Brun constant. He showed that the sum of twin prime reciprocals converges instead of diverges. And we can take a look at, say, the twin primes under 10 to the 6th, and we get this value, which is not all that close to the known values so far, 1.9. But you need many trillions of terms to get to this level of accuracy. A related item is to look at prime quadruples, such as 11, 13, 17, 19. And most of these deal with primes in some way. The sum of the Mersenne prime reciprocals is this Erdos constant. The Backhouse constant looks at a constructed polynomial, 1 plus 2 to the x plus 3 to the x squared plus 5x to the third, where you're taking the primes and repeating them in a certain way. And that has the root, this particular root here. A long prime is one where the length of the repeating decimal is equal to 1 less than the prime itself. For example, 7 has a length 6 repeating decimal. 17 has a length 16 repeating decimal, and 19 length 18 repeating decimals, 23 length 22. But 31 is not a long prime, neither is 37 or 41. 97 is a long prime with length 96. This is one of the items Gardner wrote a column about. Arden's constant is the density of long primes. And in fact, it's a conjecture, actually. It hasn't been proven yet, but it's believed to be the density of long primes. And we can get a very precise value of it using this code here. Ramanujan also came out with a bunch of constants, but they're not constants he wanted to be known for. For example, this value here was used in Martin Gardner's April Fool's joke, where he said that this was an exact value. E to the pi squared of 163 was the exact value, that with a 4 at the end. And he was corrected by many people who showed that this was actually a more complex value. So this is one of the amazing almost integers that's known. But it turns out if you look at a root of this polynomial here, x to the third plus 4x equals 6x squared plus 2, and you raise that to the 24th power and subtract 24, you get an almost identical almost integer, but it starts diverging on this digit here. This is a property of modular forms, that these weird numbers that come out of Ramanujan values also have corresponding polynomials with similarly strange properties. Another continued fraction is, or another almost integer is e to the minus 2 pi square root of 5, and it has this value, very close to 1. A value I put at the end here is Niven's constant, which is equal to this particular sum. And I forgot to figure out what this is supposed to represent. Let's see, some probability constants. If we have a whole bunch of hats scrambled and we just hand out hats randomly, we can figure out the probability of no one getting their own hat. And that is equivalent to something called a derangement permutation, where none of the values in the permutation is equal to the original value. And the expected value for a derangement in a permutation is this value, 1 over e. And if we look at order 9 derangements, we have a function for finding derangements. At order 9 the permutations for 1 to 9, there's an agreement of 6 decimal places to 1 over e. Another random one is if you start parking cars randomly along a stretch of road that's been snowed over so that nobody can see any parking lines, the amount of fillage you'll get as people just park their cars randomly is about 0.074. Another that comes out is the typical size of a cycle in a permutation is usually about 0.62 the size of the whole permutation. And I've already forgotten what I was supposed to say about Flageolet-Martin. This icon appears in the analysis of... Yes, I've forgotten what this is. Apologies for that. Some chaos constants. The logistic map has various bifurcations in it, and we can see a picture of it here. So here's a picture by Trott and Weisstein of various loops. You can see in blue. The red dots are random values in the logistic map, and these curves here in green and blue, those show where the period doublings are. And Feigenbaum was looking at these ratios between the period doublings, and he noticed that they go to this constant, and it now is named after him as the Feigenbaum constant. There's various titration constants where you stack a bunch of values in a power tower, and those will go to various constants as well. Packing constants. The densest packing of circles is the simple hexagonal packing, and it has this density here, 0.09068, or pi over 2 times the square root of 3. For spheres, the densest packing, I believe it's now proven, the Kepler conjecture, I believe Thomas Hale proved that. The densest packing is pi over the square root of 18 using the face-centered cubic packing. We can look at the density of Apollonian circles, or we can take a look at the Hausdorff dimension. And as we increase the number of steps, we get a fractal that has this particular Hausdorff dimension. I'm not sure what happens when we zoom here. Yes. So these are the Apollonian circles. Another dealing with packing is the Rouleau tetrahedron, where we basically bound a tetrahedron with spheres. And the volume of the unit Rouleau tetrahedron is this value here. If we roll around a Rouleau triangle and a square, the amount that's cut off as we roll the Rouleau triangle around is 0.9877, or this value here. If we look at the total area of Ford circles, these items here, these fractions make a Stern-Brokat tree. Basically, all the Ferry fractions are derivable from here. 7 plus 6 is 13. 13 plus 11 is 24. And these are all tangent circles. Each fraction is basically there's a way to add fractions together that, for example, 1/2 plus 1/2 would be 1 plus 1 is 2, 2 plus 2 is 4. So if you use this incorrect method for adding fractions, you get 2 over 4 as the sum of 1/2 plus 1/2. If you actually use that, you can get Ford circles which are all tangent to each other. And the total volume is given by this value here. And I posted a picture of this, and that landed me in Facebook jail for some reason. I don't understand why. But apparently it did not like, Facebook did not like this image at all. The domino tiling constant deals with the number of domino tilings, and we can calculate, these are the number of domino tilings up to, I think, order 16. And as we go get closer and closer, we can see that these are actually slowly converging to minus Catalan over pi. This is we've got almost 3 levels of accuracy at order 16. Another weird constant is the area of the biggest little hexagon. This is a hexagon where the maximal distance between points is 1. And this is something found by Ron Graham. If you look at, this is larger in area than the regular hexagon, where the distance between vertices is in the diagonals is 1. One related item is the biggest little polyhedron. For example, here's the largest. If we look at the convex hull of this, we get the largest polyhedron with 16 vertices, where these lines here are all length 1. So this is a caltrop. Here's the largest for 15, 13, 12, 11. So here's the solution for 9 vertices here. And for 8, for 7, we're basically putting in lines of length 1 for these diagrams. Length 6, because I think the rod one isn't working right. Yeah, this I need to fix the code here to get the convex hull correct. So I'll make an update for that soon. So here's 6 vertices, and the largest area for this is 1.9. Let's see. Some of the fractal constants, the Koch snowflake, we can look at the various Hausdorff dimensions. For the for this super golden fractal triangle here, which I've shown here, if you look at the whole thing, you can see that it's divided into 2 similar copies of itself. So these are scaled by the super golden ratio. We can look at the Hausdorff dimension, and it turns out to be this value. We've got the super golden ratio at the bottom, x to the third equals x squared plus 1. And we basically divide it by a companion matrix seen in Rousey fractals. It took a while to figure out that this was a order 7 polynomial, but it's a simple one. X to the 7th equals 2x squared plus 1. And that gives this value as the Hausdorff dimension of this fractal rectangle. And it's believable because this edge is rather if this was a straight line, it would have Hausdorff dimension 1. But it's slightly wriggly, so this is Hausdorff dimension 1.02. There's also a related plastic constant fractal triangle. It's a little bit more wriggly. You can see it here. And these values here, rho to the 0, that is a complex root of x to the third equals x plus 1. We've taken a complex root. If we raise it to 0, we get this point here. If we go to the first power, it's this value, second power, third power, fourth power, fifth power. And these happen to be important points on the fractal triangle. So if we look at the root of the plastic constant and take the log and use this order 5 polynomial, x to the fifth equals x plus 1. This gives the Hausdorff dimension of the plastic fractal triangle. And these two are new constants I found while putting this talk together. Salem values. I just talked about plastic constant. The first coefficient is 1, and we can take a look somewhere here in this list of 480 is the plastic constant. And I'll scroll back to that. But a different polynomial is the Salem polynomial. It has 2 roots that are off the unit circle. Everything else is on the unit circle. If you set up a polynomial that has that property where all but 2 roots are for example, all the non-real roots are on the unit circle, and there's only 2 real roots, the smallest known for the real root outside of the circle is 1.17 for this polynomial here. So this is known as the Salem polynomial, and it's unknown if that's the best one. So let me see what else we've got in here. So we've got various cyclotomic polynomials. These are polynomials where every root is on the unit circle. This is a Poisson number here. This is the plastic constant. So this is a very small value outside, and the other 2 are inside. Here's the next Poisson number. This is the super golden ratio here. Another cyclotomic. The third Poisson number, this is the chi constant. Another cyclotomic. You might notice that all the cyclotomic polynomials have coefficients that are 0 or 1. So here's the next Poisson number. It's slightly larger value on the outside. And the next. It counts as a Poisson number if this real root is less than 2. You can see there's more and more of these Poisson numbers. And as we continue to scroll out, we start getting Salem numbers and other values. So it turns out that for cyclotomic polynomials, the 105th breaks the cycle of all coefficients being 0 or 1, and because it has a coefficient of -2. And at term 385, we get a coefficient of -3. So this is a related set of weird polynomials. The Catalan constant we can calculate with this value here, and it's a alternating sum of reciprocals of odd squares. So after going up to 17 squared, we get this value, and that's somewhat close to the actual value. And here's another formulation for the Catalan constant here. Oh, and up at the top, this is how the Dirichlet beta function is defined, which is related to the Catalan constant. There was a entrance exam for the University of Bucharest that asked for a starting value which went to infinity for this repeating series. And there's a unique value that works. And if we plug in this value, which is an approximation, you can see that it's steadily increasing for quite a few turns before it starts diverging. Because this isn't an exact value. It turns out that the entrance exam made a mistake. They were supposed to post a much simpler problem, but one student named Foya solved it anyways, and now the constant is named after him because he was the only one who solved it. The Grossman constant is similar. There's a unique value which converges for this series here. Trot constants deal with repeating decimals where you have a series of digits, and when you use that as a continued fraction, you get the same digits 0, 0, 1, 1, 0, 0, 8, 8, and so on. There's several of these values which are both a decimal and a series of digits in a continued fraction. Percolation is where you take a infinite grid and you wait for a certain property to appear, such as an infinite cluster or an arbitrarily large cluster. That's what's called a critical threshold. So for various infinite grids, for example, a cubic grid, if the bonds or vertices? If the edges are randomly being filled in with this probability, you will eventually get infinitely large clusters. And if the vertices are the ones being randomly filled in, all edges are present, but the vertices are not, you get the cubic site percolation probability. At this probability and higher, you'll get infinite sizes, and at that probability and lower, you will not, usually. And there's different percolation thresholds, both vertex-based or site and edge-based or bond for any infinite lattice. Linear recurrence growth. For example, here we have the Fibonacci sequence and the Fibonacci sequence. The linear recurrence constants are basically extensions of the Fibonacci sequence constant, or the golden ratio. If we look at the Fibonacci sequence, their ratios go to the Fibonacci constant, and we can keep bumping that up to order 4, order 5, or and so on, and we get the Tetranacci, Heptanacci, Hepkexacci, and so on. It turns out that if we look at the Fibonacci constant in itself, which is this value here, about 1.84, we can build a snub cube out of it using just one over the constant and the constant, and various sign permutations of that will give the snub cube, which is shown here. Gardner also wrote about logarithms, and quite a few of the constants we have in our table are logarithms. So with using this is a short demonstration about the property of logarithms. And logarithms are handy because you can take the log of a product and split it up to make a sum, which is how slide rules work. Are various numbers transcendental? The seventh Hilbert problem asks about e to the pi and 2 to the power of the square root of 2. And a person by the name Gelfand came up with a theorem that showed that these were transcendental. So both of these values got named after him because he proved that they were transcendental. The next major value that was proved transcendental was Avery, who managed to prove that this value here, which is the sum of cubic reciprocals, he was able to prove that that was a transcendental number. And that's how he became famous. Euler similarly became famous for solving the basal problem, which was the sum of square reciprocals, which is now known as zeta of 2. And he proved that it's equal to the pi squared over 6. And that's known as the basal problem. So the first two have been solved. The next one is zeta 4, which is also solved by Euler. But whether zeta 5, the sum of quintic reciprocals, it's still unknown whether that's transcendental. Excuse me, I'm gonna get a drink of water here. Okay, numbers are carefree if they are relatively prime, and one of them is square free. And we can make a pattern of these. Oops. Let's change this to 7. We get this weird pattern here for carefree numbers. The percentage of black squares here is the carefree constant. And we can change how these are defined. Like, what if they're both square free? Or what if either is square free? We get various different ways of representing the carefree constant. For example, the strongly one and so on. Let's see. The abundant numbers is the density of values that have the sum of the divisors is greater than the number itself. Is what an abundant number is. So with this constant, we can predict that less than 10 to the 6th, there are that many abundant numbers. And when we do the calculation, we see that we get more than that. 795 instead of 762. So, but that's still reasonably close. So that's how the abundant number density constant works. Search trees. I wasn't able to come up with a good way of showing how these search trees work. But these are some of the constants dealing with searches. For example, the beta constant is equal to this particular value known as this Erdos-Borwein constant. Here's a constant I did some research on last month. If you look at a toy xylophone, for example, this one here, there's various holes drilled at the 2/9 points on either side. And that's because if you put fine salt on a bar and let it vibrate, the fine salt will make lines at approximately 2/9 from each end, part of Chladni patterns. So those became known as the 2/9 points, and those were the ideal places to mount bars in a xylophone or glockenspiel or vibraphone. And later, physicists found that the actual value is actually closer to 0.224. So that's became the standard value for drilling these points, 0.224. But you can actually apply some math. You do the hyperbolic cosine and regular cosine. You solve this, and then you plug that into these values here, and then you find this root of hyperbolic sines and cosines, and you end up with this value here. So that's something I recently added to the online encyclopedia of integer sequences. It went live yesterday. So this is an actual constant. This is the actual value of the 2/9 constant. It's not 2/9. It's 0.224157522 and so on. But that extra accuracy won't help at all when you're drilling a big hole into a metal bar. So the 0.224 is good enough. Pythagorean triple constants. These deal with Pythagorean triples, and Lamer showed that the fraction of primitive triples with a perimeter less than p is this value here. And we can plot that out here, and you can see that it is going to that constant as we run this code. So we've got about 4,000 triples here, showing that this perimeter constant is correct. We also have things like the square root of 3 and so on. I forget who it was. Hippasus, I believe, showed that the square root of 2 was a rational, and the Pythagoreans rewarded him by throwing him off the boat so he would drown. They killed him because they didn't want the square root of 2 to be irrational. Geometric constants. The Steiner ratio of the Euclidean plane is basically based on this diagram. They want to know what the minimal Euclidean spanning tree. So here's a spanning tree of 3 points for a equilateral triangle, and here's the Steiner tree connecting these points. The ratio between just connecting, these are sometimes seen as town connecting problems. So the minimal distance for just connecting the town straight, and the minimal path for allowing extra points to be used, the ratio is 2 over the square root of 3. And it's believed that that is the worst case for any set of points. So that is the Steiner ratio of the Euclidean plane, is the ratio between these two diagrams. The $100 100-digit problem was something I got the chance to work on back in 2002, and there's a good paper on these 10 problems in experimental mathematics. It turns out that 20 different teams solved all 10 problems perfectly, so the prize was awarded to all 20 teams. I was part of the Wolfram team, but I don't know what happened to the money in that. I think that must have gone to Michael Trott, since he was the one who solved, I think, 8 of the 10 problems. Picking constants. A random chord drawn in a unit circle. That is the circle line picking problem. And it turns out the average chord length is 4 over pi. So each of these deals with, you have one random object that you place inside of another object, and you want to know how big it is on average. And that gives the picking constants. And each of these gives a particular value. For example, the disk line picking problem, if you have 2 random points in a disk, the average length of that line is 128 over 45 pi. And if you take a random line in an equilateral triangle, you get this as the average length of the line. So these are various values. For example, if you have 2 points on the face of a cube, you get this very complicated value for the average length of the line. Various trig constants. The Fafan constant is basically the odds that equally spaced lines, if you just randomly toss needles on the lines, whether or not one of those, whether or not a needle will land on one of those lines. And it has the constant 2 over pi. These are all various related to pi or something similar in some way, or to trigonometry. For example, the Dottie number, if you take a calculator and you put in any number, for example, we'll say 2, and you just press the cosine button over and over and over again, you'll get this value here, which many people did, but it was a French professor by the name of Dottie that the constant got named after, the fixed point of cosine x equals x. The magic angle is a cube edge to the main diagonal, and the tetrahedral bond angle is the angle seen in a tetrahedron. The Conway constant, if you do 1, that can be said as 1, 1, and then the next term here can be expressed as 2 1s, and then the next one has 1, 2, and 1, 1, and so on. This is called the look and say sequence. John Conway figured out the limiting growth is based on this order 71 polynomial. I think I said it was order 72 early in the talk. Well, it's order 71. And we can plot out the roots of this polynomial. And this is the growth value over here. And these other points are other complex roots. So that's this value here is now known as the Conway constant. We also have various physical constants, and I've shown this slide a few times. All of the base constants are now fixed quantities as of November 16th of 2018. And they all fit together very well. And I gave a talk about these measuring the universe, where I talked about these values and others. But there's a lot of physical constants. In fact, we have over 400 of them, and here's some of them here. Maybe I should do a talk on these as well. We also have a page discussing some of the physical constants and how nice it is that everything is a rational value now. So I didn't have time to go into physical constants. In fact, it looks like I've already gone over. We have a whole bunch of unsolved problems with constants. And here are some of them here. Whether various values are transcendental, what are some of the exact values? For example, the Moser-Worm problem is bounded. The best spear packing in 5 dimensions is bounded. The order 3 Grothendieck constants are also bounded. So here are a few of the unsolved problems that I know about. And that's all I had. You can write to me if you'd like to. And this will be available at community.wolfram.com sometime today or tomorrow. And that's what I had. If anybody has any questions, I'll be glad to answer them. All right, many thanks.